Okay, good morning, everybody. It's time to start our Friday. All right, so today we're talking about what are called Riemann sums. And that's Riemann. He was a German dude, so you say his name Riemann, okay? All right, so some announcements. You got homework due Monday night. Really, there is not, if I remember right, there aren't any limits of sums on the homework. So really, you should be fine to do it before this class, but definitely after this class. And then there's a quiz due tonight. I opened it on Thursday, so make sure that you get it done before midnight. Shouldn't be very tough. So if you are running into any trouble, let me know, and I will help you out with that. Okay. So there's two things I want to mention before we start. Thing one, on Tuesday's lecture, I forgot to mention, I used it implicitly in Thursday's lecture, but someone emailed me and asked if I meant to forget this. I did not mean to forget it. So with sums, there are two sort of properties that, again, I used implicitly. I didn't explicitly state them. So, so first, that the sum I equals 1 to n of some constant times, that constant is bad, some constant k times terms that involve the index variable I. This is just equal to, you can pull that constant out in front. And I used this implicitly on Thursday. So the idea here, just think of if you had k times 1 plus k times 2 plus k times 3 plus k times 4. If you had that, all this is saying is that you can factor the k out. That's all that's saying, is that this is equal to k times 1 plus 2 plus 3 plus 4. That's all that's saying. Okay. And then the second property that, again, I implicitly used, but I forgot to explicitly state it. But again, it's something that you should be familiar with already just from working with numbers and sums. Okay, so the second property was the sum I equals 1 to n of ai plus or minus bi, that this is equal to, well, you can do these sums separately. The sum I equals 1 to n of ai plus or minus the sum I goes from 1 to n of bi. Okay. So again, you can think of this as, if you're looking at something that looks like, I don't know, 1 plus 2 plus 2 plus 3 plus 3 plus 4 plus 4 plus 5. If you're looking at something like that, all this is saying is that, well, not equal, but plus the equals. This is all this is saying is that I can add all the first terms in each term. I can collect all those guys together. So this would be 1 plus 2 plus 3 plus 4 plus, so that was all the first pieces of this, plus 2 plus 3 plus 4 plus 5. So this is sort of a generalization of what's called the associative property, or in combination with the commutative property of addition, right? You can add, all this is saying is that you can add things in whatever order you want, okay? So those are two properties of sums that I used implicitly on Thursday. I didn't state them explicitly because I forgot, well, I ran out of time on Tuesday, okay? All right, and then the one other thing, I just want to remind us of the picture of what's happening with what we're talking about today, okay? So, as a reminder, what we're trying to do straighten out, come on. What we're trying to do is, whatever, that's good enough. Perfect. Is find, if I have some, right now, positive function, some function that lies above the x-axis. This is y equals f of x. Okay. What we're trying to do is find the area underneath this curve and above the x-axis. Okay. If anyone asks you, what are you doing in Calc 1 this week and next week and the week after, you tell them, I'm finding the area under a curve. That's the goal. Okay. And so how do we accomplish this goal? Well, the idea is I'm going to use in rectangles. In rectangles. Well, what is in? In's a variable number of rectangles. For any one sum that we're looking at, in is fixed, but then we're going to let in get very, very, very big. Okay, so I'm using in rectangles in a width. I'm trying to fit these in rectangles in an interval of width b minus a, right? So that means if I draw in one of these rectangles, and again, for right now, we're looking at rectangles where their right edge goes up to the curve. Okay, so the right edge comes up to the curve and then over. And then the right edge comes up to the curve and then over. And the right edge comes up to the curve and then over. Like this. Okay, so each of these rectangles, I want them all to have the same width. Does that have to be the case? No, but that's what we're going to do. I want them to all have the same width. And that width then is going to be b minus a divided by n. I'm trying to fit in rectangles into a length of b minus a. Okay, so this is what we're going to call delta x. Okay, so again, this width right here, delta x. All right, then I'm going to draw some dots, and I'm going to draw in a general rectangle here. So here is a general rectangle. Its height here, well, if I've taken k steps away from the start, its height at that right edge, the height of the rectangle is, well, that's just f of x k. I've taken k steps away from a, that's f of x k. And so really the only thing I need to do if I want to find the area of, I'll color in red, if I want to find the area of this one individual rectangle, which sort of represents all of them, this is just a general rectangle, then I need to know, well, what is the width of it? Well, all these rectangles have the same width, right? All these rectangles have a width of delta x. And what is the height? Well, that's just f of xk. So really, I just need to know what is xk. So xk is equal to, well, when I've taken 0 steps from the left edge, then what point am I at?
Delta x.
I'm not
a plus delta x.
That's if I take 1 step away, right? If I take 0 steps away from a, then where am I? I'm just at a, right? So x0 is just a. And then, yeah, x1, you're exactly right. I've taken a step of delta x, and so I'm at a plus, I'll say, so that we can see the pattern, we're at a plus 1 times delta x. Okay. x0 is really, we can write that so that I can really see the pattern. x0 is a plus 0 times delta x, right? What's x2? A plus 2 times delta x. What's x3? A plus 3 delta x. What's xk? Perfect. A plus k times delta x. Okay, so the width of this rectangle, this general rectangle here, is delta x. The height is f of xk, and so we can actually say that that's f of a plus k times delta x. Okay. That's the height, yeah, f of a plus k delta x. And so the area of that individual general rectangle is this. And so to find the area of the sum of all of those, well, because this was just a general one, I can just put the sum sign in front. Okay, and I'm using the right edges. So k is starting at 1 and ending at n. Okay.
Can you kind of repeat where you got that height from and the sum, you added the sum in front of it or behind it?
Yeah, so I'll erase the sum really quick. So you want to know, where does this come from?
Yes.
Okay, so that comes from, if we look at the graph, the height of this general rectangle, do you agree that that's f of xk?
Yes.
So xk then, if we come down here, x0, to find out what xk is, that's when we've taken k steps away, k delta x steps away from a. Okay, so x0 is a, x1 is a plus delta x, x2 is a plus 2 delta x, and in general, xk is a plus k times delta x. So all I've done, this is the area of this rectangle. So all I've done is I've replaced xk with its definition, a plus k times delta x. Okay.
Gotcha. Thank you.
Yeah, of course. And then again, this is what a general, the area of the general rectangle looks like. So I can just add all of these up.
So when you do this for an example, obviously that's like area equals height times the width.
Yeah.
For the delta x, is that just how many rectangles there are when you're doing the example?
Good question. The delta x is going to be b minus a divided by how many rectangles there are. Yeah. Right there. So yeah, so whatever our index variable is, that's what we need to know where we start it. And because again, we're starting at the right edge of the first rectangle, that's the right edge there is x1. That's where we're starting. So we're starting with k equals 1, and we end with k equals n when we're over here at b. When k is n, well, then xn is a plus n times b minus a over n, which simplifies to b. Okay. So that's the picture that you need to keep in mind when we're doing everything that we're doing. Really, I mean, it seems complicated, and it in general, finding the integral is harder than finding the derivative. I will not lie to you about that. But at the heart of it is we're just finding the area by using rectangles and then letting that go to infinity. Okay. So I think there was one other note in the chat. Newton's method was not in the recording. Yeah, I decided to scrap Newton's method. So just so everybody knows. Okay, so last time we left off here. Approximate the area under the graph of the function f of x equals 3x plus 4 between x equals 0 and x equals 5 using n equals 5 rectangles, n equals 10 rectangles, and just n rectangles. Okay, and our answer then is going to depend on n when we do that. Okay. So by the way, this is called the right hand, because we're using the rectangle's right edge. This is called the right hand sum, just so you know. Right hand sum. Okay. So let's use n equals 5 rectangles in with the right-hand sum. Okay, so wow, I did not leave myself any room. Add page. Here we go. So let's first get a sketch of the area that we actually are trying to find. We want the area under the function f of x equals 3x plus 4. Well, that's just a line that crosses the y-axis at 1, 2, 3, 4, and has a slope of 3. So x, comma, y has a slope of 3. So up 1, 2, 3 over 1. There we go. Draw it. Cool. Between x equals 0 and x equals 5. I did not leave myself much room up top there either. Okay, this is going to go way off the screen, but you get what we're trying to do. So 1, 2, 3, 4, 5. So I'm trying to find here this area of this. Really, we don't need to approximate this, right? There's a couple of ways that we can find this area. We could, if you know off the top of your head, the area of trapezoid, that's all this is. This is a trapezoid, right? If you don't know that off of the top of your head, that's okay. Not many people do, but you could also recognize that this is just a triangle stacked on top of a rectangle, right? And so you could also find the area of the upper triangle and the lower rectangle and find the exact area that way. So we don't actually need calculus for this problem, but we're still going to use the sums to approximate it. Oops, and it's nice to do this with something where we know what the answer should be. So the answer should be 1, 2, 3, 4, 5 times 1, 2, 3, 4. It should be 20 plus 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 20 plus 5 times 13 divided by 2. It should be that, right? So this is the exact answer. We want to make sure that our answer is close. So first we're going to use 5 rectangles. So let's draw them in. Okay, I'm using 5 rectangles. I'll draw them in blue. I'm using the right edge. Well, first of all, what should delta x be? If I'm trying to fit 5 rectangles into this interval of length 5, the interval from 0 to 5, how many rectangles, or what should the width of the rectangles be?
1.
It should be 1. Yeah. And I get that from 5 minus 0 divided by the 5 rectangles I'm using. Okay. So I start at 0. I come over a step of 1, and then I draw in this rectangle. Now, could I have made the left edge go up to the curve instead of the right edge? Yes, that's called the left-hand sum, and we'll look at that in a minute. And actually, in general, you can pick any point in between your left edge and your right edge to be the point that goes up to, oh great, to be the point that goes up to the point that goes up to the function itself, okay? But in general, we're going to use the left and right edges. So here's rectangle number 2. I go another step of 1. There's rectangle number 2. I go another step of 1. Rectangle number 3. Okay. Rectangle number 4. And rectangle number 5. Okay, so we could use the graph to get these areas, to get these heights, but my drawing's not perfect. There's a little bit of error. Let's look at what these heights actually should be. So first, this is 1, 2, 3, 4, and 5, right? Those are my right endpoints for each of these rectangles. So for rectangle number 1, what's the area there? Well, I'm going to have delta x for all of these. Delta x is 5 minus 0 divided by 5. So delta x is 1. I'll write delta x in to be, complete. But let's say then I'm looking at f of 1 as the height. Okay. Well, what is f of 1? Not from the graph, but from the function. We know the function f of x is 3x, 3x plus 4. So f of 1 is what?
7.
7. Very good. So this is going to be 7. Okay. Then I'm going to do plus. What's the next function value I need to evaluate?
F of 2.
F of 2. Very good. And so f of 2 is 6 plus 4 is 10. Plus, then I go over to f of 3. Because again, I'm looking at this height. So the first height I was looking at was f of 1. Then I'm looking at f of 2. Now I'm looking at f of 3 to get the area of this rectangle. By the way, really quick, is our answer going to be an overestimate or an underestimate that we get here? Yeah, it's going to be an overestimate. And why? Exactly. We're getting this little bit of overestimation here with each guess. Okay, so our answer is not going to be exact, but it should still be decently close. So next I want f of 3. Well, that's going to be 13 multiplied by delta x plus, then I want f of 4. I'm running out of room. Well, f of 4 is 16, and I won't bore you guys with the arithmetic. I know you know how to do arithmetic. So, I mean, slope is 3. Every step you're just adding 3, right? Okay, so I want this plus this plus this plus this plus this. Okay, so that's going to give me 17 plus 13 is 30 plus 16 is 46. 46 plus 19 is 50 or 65, right? 65. Okay, so we got 65 there. Questions on that? So these questions about estimating area with either a left or a right hand sum. With the left hand sum, you just use the left edge, but this is it. If they give you a fixed in, like that's it. You just do this. It's as simple as calculating the area of a bunch of rectangles and then adding it up. Okay. So part B, we wanted to know. Part B, we wanted to know what if we're using n equals 10 rectangles. Well, if we're using n equals 10 rectangles, then what is delta x? Now I'm trying to fit 10 rectangles into this length of 5.
Delta x minus 0 over 10.
Careful, well, it's still the interval 0 to 5. So yeah, it's 5 minus 0 divided by 10. Very good. So 5 minus 0 divided by 10. So that's 1/2. Okay. So then let's try and do this one a little more generally without looking at the graph. Let's look at what is xk. Well, remember, xk is always k steps away from where you're starting from your starting point. Okay, so xk is going to be our starting x value is 0 plus, well, then I take k delta x steps, and how far away is that going to be? So what is k times delta x going to be in this case? Plus 1/2, right? Yeah, so 0 plus 1/2 times k is just going to leave me with k over 2. Okay, that's k steps away, xk. Okay. So then now I can write down sort of the general form of the sum. A general rectangle is going to have, we remember that the general rectangle has a width of delta x. That's going to be true no matter what you're looking at. And then the height is going to be f of xk. And that's also, if your function's called f, that's also going to be the height always. If you're looking at the left-hand sums, then you're just looking at, instead of f of xk, no shock here, it's just going to be f of xk minus 1 because you're using the left edge instead of the right. But we're using the right-hand sum, so this is just f of xk. Okay. And then we're going to take the sum, k equals, well, k is starting at 1. I'm starting with the first right edge, that's x1, and k is ending at n. And what is n for us in this example? 10. Very good. So then now I just need to fill in what this actually is. This is going to be the sum, k equals 1 to 10. What is f of xk? Well, f of x, remember, f of x is 3x plus 4. So f of xk, well, that's f of k over 2. So what is f of k over 2? So this just means everywhere you see an x, plug in a k over 2, right? So I'm going to get 3 times k over 2. That's 3 times xk plus 4. Okay. So that's f of xk, which again, xk is k over 2. So I'm going to get f of xk is 3 times k over 2 plus 4. And then this is all times delta x. Delta x now is 1/2 because we increased the number of rectangles. So then this is equal to the sum k equals 1 to 10 of 3k over 4. Well, there's two things you could do. You could distribute the 1/2, or you could pull it out in front of the sum, right? Either way, you're going to get the same thing. 3k, I'm going to distribute it. 3k over 4 plus 2. Okay. Questions on that? We can evaluate this now. When we evaluate this, we get the sum, k equals 1 to 10 of 3 times k over 4 plus 2. Well, this is the sum, k equals 1 to 10 of, I'll pull the 3/4. Well, let me break this apart in 2 steps. This is 3k over 4 plus the sum, k equals 1 to 10 of 2, right? That was that second property that I mentioned at the start of class. And then this is then equal to this 3/4 times the sum, k equals 1 to 10 of k. The 3/4 doesn't have a k. I can pull that out in front. Everything with a k needs to stay inside the sum though. And then plus the sum, k equals 1 to 10 of 2. Okay. So this is 3/4 times. This is one of those special sums that we needed to remember. And this is why we need that special sum, because it comes up when you're finding the area under a linear function. Okay. So this is 3/4 times, well, this is the sum from 1 to 10 of k. That's 10 times 10 plus 1, which is 11, divided by 2. Again, that's one of those special sums that I don't really expect you to have memorized at all. It's nice if you do, but you don't need to have it memorized. And then plus, what is this? I do expect you to know this one. What's the sum of 2 where k goes from 1 to 10? $20, yes, thank you, Saba. We get 20 because this is just 2 plus 2 plus 2 plus 2 plus 2, 10 times, right? That's 10 times 2, that's 20. Excellent. So this is then equal to, well, I can cancel a 2 here with a 2 here. So I have what, 55 times 3, that's 165 divided by 2 plus 20. Okay, this is closer to the actual answer of 5 times 13 over 2 plus 20. Okay.
Should that be 165 divided by 4?
Oh, yes, thank you very much. Yeah, it's 2 times 2 there. Thank you very much. That makes it even more close to the actual value of the area, okay? And so, because we did this kind of generally, I mean, we plugged in n equals 10, but really we did it pretty generally until we plugged in n equals 10. We can actually just use what we just did. We need to change a few things, but the process is the same for just using in rectangles, okay? So for part 3, if we're using in rectangles, just a general in, then what's going to be delta x? And it's going to depend on n. I'm trying to fit in rectangles into a length of 5.
Five minus 0 over n.
Perfect. 5 minus 0 divided by n. It's the length of the interval divided by the number of rectangles. That's still the case, even if they're rectangles. I'm just using a general n. So this is 5 over n. Okay. So then what is xk? We need to know what xk is. Well, again, xk is when we've taken k steps away from 0. So it's going to be 0, and in general is whatever the left endpoint is. But here that's 0 plus k steps away of delta x. So 0 plus k times delta x for this case. So that's going to be, what's that going to simplify to? Perfect. K times 5 over n, which I'm going to write as 5k over n. Perfect. Okay. And then the only other thing we really need in the sum, I need to know, we're using the right-hand sum. I need to know what is f of xk. Well, that's going to be, remember, f of x is 3x plus 4. So f of xk, that's just going to be 3 times 5k over n. There's the first part of f of xk, and then I add 4. Okay. So, and again, draw this out as often as you need to, by the way. If you need to draw it out each time, do it, be my guest. I think we're going to do this often enough that eventually you won't need to, but until you feel really comfortable with it, definitely draw it out every time. So the area of a general rectangle, again, the height is the function value at the right edge, that's f of xk. The width, it's fixed for each rectangle, delta x. So I'm taking then the sum of all of these guys. The sum, k is still starting at 1. I still want my first height to be x1, f of x1. So k equals 1 to n. Okay. Of f of xk times delta x. Good question. F of x here, I just gave it to you. I said find the area under f of x is 3x plus 4. So there's nothing special about 3x plus 4 other than that's what I gave you for this problem. Okay, so this is equal. Now we just plug everything in. Okay, we don't have an n again because that's kind of the point of this is find out what's happening for general n, and then we're going to do something very special. Okay, f of xk, well, that's this guy right here. 3, I'll simplify this to 15k. 15k over n plus 4. There's f of xk, and then delta x, well, that's 5 over n. Delta x is 5 over n. So we're almost done. We're almost there. I want to simplify then. Technically, this is an answer, right? Technically, this is an answer, but we can do a little better. We can simplify this. So just like the last one, I can say this is the sum k equals 1 to n of 15k over 3 plus, times 5 over n squared times 5 over n squared.
Where did 3 come from?
15k over, sorry, that should have been an n. Yeah, that was my bad. Hold on, let me restart that. Going back and forth got me mixed up. I'm gonna copy and paste this instead of going back and forth. Paste. There we go. All right, so this is what we want to simplify. This is equal to when we distribute, or when we, I'm going to pull the 5 over n out this time. So this is 5 over n times the sum k equals 1 to n of 15k over n, not 3, plus 4, right? So then, just like last time now, I can break this apart. So this is still 5 over n out in front of everything, times the sum k equals 1 to n of 15k over n, plus the sum k equals 1 to n of 4. Okay. This is then equal to 5 over n times, I'll pull the 15 over n. N does not depend on k. Okay, so I can pull out 15 over n times the sum k equals 1 to n of k. And then plus, what's the sum of k equals 1 to n of 4?
4n.
4n, very good. Okay, so this is then equal to 5 over n times 15 over n times the sum k equals 1 to n of k. That's again n plus 1 times n divided by 2. And then this is all plus 4n. Okay.
Did you go over the centerpiece then, this 1 times 1?
Yeah, so that's one of those special sums that that I gave you guys. But yeah, the proof was just this. If s is equal to that, s is equal to that also. So yeah. Okay. We can simplify this more if we want. I'm not going to. I'm going to move on because that. I mean, these problems do take a while, but it's worthwhile to see that. Okay. But in the end, what do you think we're going to do now? Now that we have this. We haven't really done any calculus yet, right? What's the calculus thing that we should do to this now? Yes, I should take a limit. I should let the number of rectangles get very, 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 very big. Or in other words, you could also think about it as letting the width of the rectangles get very, 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 very small. Okay, so that's what we're going to talk about on Monday. So a really quick note, we could have just as easily used the left edge of those rectangles to end up with another approximation. It will be different. It will be different, especially for that last problem. We had overestimates with all of my rectangles. If I use the left edge, that's going to give me underestimates for every rectangle. Okay, so it's definitely going to give you a different estimate. In sigma notation, the left-hand sum instead of the right-hand sum, the left-hand sum using in rectangles of width. All of our rectangles are still delta x minus delta x equals b minus a over n width, and we're still using the function as our height, but now I'm just using the left edge. Okay, so all of the function values then are f of x equals, instead of, okay, there we go. Instead of f of xk, well, let's look at a drawing again really quick. A, B. A is, by the way, x0. Here's x1, x2, x3. So now I'm using left edges. And pretend these are all equal width. Okay, so here's a general rectangle. This is xk minus 1, xk. Okay, so now instead of using the right edge, we're using the left edge, right? So one way you could write it is as the sum k equals 1 to n of f of, well, now for this general rectangle, I'm coming up to the left endpoint. So that's f of xk minus 1. And then times delta x, okay? All the xk's, all the delta x, those are all still defined the same way, okay? Another way you can write this, well, instead of using xk minus 1, we could just say, well, I'm starting the sum at x0. Why wouldn't I just start k at 0? And then you could just say this is the sum k equals 0. And then we're stopping not at b. The last function value is evaluated at x in minus 1, right? So you could also write it like this. And this is usually the way I will write it. Okay. You just, all that really needs to happen is you need to keep track of the left and right endpoints, what's happening. And that's a very good note, Saba. For a general function, both of these sums, you can't say in general which one's going to give you an overestimate and which one's going to give you an underestimate. For an increasing function, the left-hand sum will give you an underestimate and the right-hand sum will give you an overestimate. But for a general function, you don't know which one's going to be more or less. They both could be underestimates. You just don't know. Okay. So either of these you could call the left-hand sum. Okay. So use the left and right-hand sums to approximate the area under the graph of the function f of x equals 2x squared plus 2 between x equals 1 and x equals 2 using n equals 10 rectangles. Okay. So let's start this. We're not going to get all the way through it, but that's fine. So Monday, we're actually going to talk about what we actually do with these when in taking the limit to get the actual area under a curve. Okay, so but let's look at this function here. What is delta x in both cases, both the left and the right hand sum? Well, if I draw this out really quick, I'm going from x equals 1 to x equals 2. I'm doing something like, there's my function. This is what I'm trying to find the area of, right? And so I'll come over, here's a general rectangle. What is delta x? I'm
Would it
trying
be
to,
1/10?
yeah, good. I'm trying to fit 10 rectangles into an interval of length 1, which is 2 minus 1, right? So delta x is 2 minus 1 divided by 10, which is 1/10. Very good. What is xk? Again, xk is when we've taken k steps away from my left endpoint, which last time was 0, but now it's not. So first of all, it's always going to involve the left endpoint. So what's the left endpoint? Where am I starting drawing all of these rectangles? Yeah, 1. And then I take k steps away. So what is k steps away from 1? Like,
1/10 K.
yeah, very good. K times 1/10, right? I'm taking, when I say k steps, I just mean k delta x steps. So that's 1 plus k/10. Okay. All right, and then lastly, we need to know what is for the right-hand sum. We're looking at f of xk, right? So what is f of xk? Well, we're just going to plug in this guy into f of x, right? So I'm going to get 2 times 1 plus k/10 squared plus 2. Okay. For my left-hand sum, I'm going to need f of xk minus 1. Well, that's just plug in k minus 1, right? So this is 2 times 1 plus k minus 1/10 squared plus 2. Okay, so then this general rectangle, let's start with the left-hand sum, because that looks, the way I drew it, it looks like I'm doing the left-hand sum, right? So what is the height of that rectangle where the left edge here goes up to the curve? Well, that's f at which x value? So I'm coming up from xk minus 1, right? So this is just f of xk minus 1. Okay. So the height of that general rectangle there is f of xk minus 1. Again, we're doing the left-hand sum first. The width, well, the width of any of these rectangles is going to be delta x. And so the left-hand sum is going to be the sum from k equals 1 to n of this guy. Yeah, n is 10. Thank you. Yeah, we'll do, I guess if you want to be specific, we can do 10. Okay. So then we'll plug in, I'll plug in that later after class before I upload these. For the right-hand sum, what's going to change? It's going to be the sum k equals 1 to 10 of, what's really the only thing that changes?
It should just be f of xk.
Perfect. It's just going to be f of xk instead of f of xk minus 1. Okay. And like I said, I'll evaluate these before I upload them after class, okay? So that you can see the explicit computation, but you're just plugging in what we found here into these sums. Okay. All right, so are there any questions about anything we went over today? Again, on Monday, we're gonna pick up here and start talking about what we actually mean by the area under a curve. And really all it's gonna be is we're gonna take a limit of these sums that we're finding, okay? So that's what we're gonna do Monday and really kind of for the rest of the semester, okay? But if you feel overwhelmed, don't worry, there's a much easier way to calculate these things, okay? And so we're going to learn about that next week. There's a much simpler theorem that we can use to help us calculate areas under curves. So don't feel overwhelmed if you do feel overwhelmed right now. I promise it's going to get better, okay? All right, thank you all for being here. I will see you next week. Get the quiz done. If you want points, points are great.
Thank you.
Thank you.
Thanks.
Thank you.
Thank you.